Hello everyone, my name is Afia Ayman. Today I'm going to talk about the data-driven prediction of route level energy use for mixed vehicle transit fleets. This work is supported by Department of Energy USA. According to 2019 energy usage data in the USA, transportation is the second largest sector, which accounts for 28% of total energy use. And it is responsible for immense environmental impact, including the air pollution, greenhouse gas emission, etc. Switching from personal vehicles to public transit system can significantly reduce energy use and environmental impact. However, even public transit systems require substantial amount of energy. As for example, in 2019, the public bus transits in the US are responsible for around 20 million metric tons of carbon dioxide gas emission. Electric vehicles can have a much lower environmental impact, especially in urban areas. It has several benefits. The most important one being the lower energy consumption, hence lower cost. It also has non-existent tailpipe emission. Also, the maintenance costs are significantly lower. But they have some drawbacks as well. One of them is the capital cost. The agencies need to pay a difference of $250,000 if they want to buy an electric bus instead of a diesel one. Also, there are other limitations such as the limited battery capacity and limited driving range. Because of these challenges, most public transit agencies operate mixed fleets of electric and diesel vehicles. So the operation of the fleets has to be carefully planned, and this is very crucial for transit agencies that operate mixed fleets. Firstly, the agencies need to schedule when to charge the electric vehicles during the day, considering a few factors, such as how long the bus can operate without recharging and when the electricity prices are lower, things like that. Secondly, they need to decide which vehicles should be assigned to serving which transit trips. Since the advantage of electric buses over diesel buses varies depending on the route and time of day, the assignment can have a significant effect on energy use and hence environmental impact. To investigate further, we started looking at the correlation with features such as traffic, weather, time of day, etc. On the left, we can see a heat map showing electric vehicles operation on different routes during different hours of the day. On the right, you can see the same distribution for diesel vehicles. The scales of the heat map are different because of the difference in energy consumption magnitude between electric and diesel buses. As you can see, for the diesel vehicles on Route 21, the diesel vehicles are more affected by time of day, and this is a good surrogate for traffic, and hence we can conclude that the diesel vehicles are more sensitive to traffic. It creates a hypothesis that we might want to assign more electric vehicles to trips that will occur in routes with heavy traffic congestion. In short, the efficient planning for trip assignment, charging schedule, and so on is very essential for the transit agencies. So one of the primary goals of this project is to enable the agency to minimize their energy use through operational optimization, including the routing and scheduling. And to perform such optimization, we need to predict how much energy a transit vehicle will use on a given route at a given time. We have partnered with CARTA, which is the Chattanooga Area Regional Transportation Authority. We have been using their vehicles' trip level data for this project. There are numerous challenges in handling this large-scale, high-resolution data, and for the prediction effort, the challenges include the data collection, data management, data cleaning, feature selection, and so on. So the primary contribution of these projects are the following. We collect and combine vehicle telemetry data, elevation data, weather and traffic data, and we present a cloud-centric data collection and storage framework. We also present a framework and some novel algorithms for cleaning and integrating the time series data. And then we train different machine learning models on the data set and study their performance. First, I want to talk about the data sources that we have been using. To collect data from CARTA's fleet of vehicles, we partner with Vericity. Vericity is a real-time data source. It offers sensor devices and an online platform to support the transit operators with real-time insight into the fleets. They have installed sensors on CARTA's multiple vehicles and have been collecting data continuously at 1 second intervals since installation. We also gather our weather and traffic data from real-time data sources using Dark Sky API and Here API. We use a static data source for elevation data. Here are some more details into the data sources that we have been using. For the different types of vehicles, we are using two types. One is diesel and another is electric. And for both types, we are working with 3 vehicles, and our data set ranges over 7 months. And for each vehicle, we obtain time series data from Veracity, which includes a series of timestamps and vehicle location based on GPS. For electric buses, we include features such as the battery current in ampere, battery voltage, battery state of charge, and charging cable status. For diesel buses, we consider fuel level and the amount of fuel used over time in gallons. We collect our traffic data at 1 minute interval using the Here API and collect the weather data from multiple weather stations in Chattanooga at 5-minute intervals using the Dark Sky API. And we collect static GIS elevation data from Tennessee Geographic Information Council. There are numerous challenges in working with high-velocity spatiotemporal data streams. Therefore, we implemented our own general-purpose data architecture framework. The data storage level consists of a pub/sub layer for handling the real-time data streams, where each stream is labeled with a topic, and downstream structured views that include merged data representation. Here is a figure where we present the implementation details of the data architecture. We use the Apache Pulsar for the pub/sub layer, which runs in VMware cluster hosted at Vanderbilt University. The structured data is stored in MongoDB running on Google Cloud. We have chosen MongoDB for its high scalability and native geospatial indexing functionality. Now, this is the data processing workflow. Before we can apply machine learning models, we need to perform a number of data cleaning and preparation steps. Our workflow starts with vehicle telemetry data, which we can retrieve from our data storage framework. And to join this data with other sources, we need to clean it first. And finally, when we have generated the clean samples from our vehicle locations data, we join them with a variety of other sources such as elevation, weather, and traffic. Finally, we split the samples into different training and test sets and apply machine learning models and study their performance. I'm going to talk more in detail about the data processing workflow in the next few slides. The first step is to remove the garage location. Since our goal is to predict the amount of energy used for driving, we remove all the data points when the bus is in the garage or the bus is charging. We check this by the status of the charging cable from the electric vehicles. For electric buses, then our next step is to compute the energy. We can use the state of charge from what we can collect from Veracity, but the state of charge values are recorded with a low precision of only 1 digit after the decimal point. So to obtain more accurate values, we need to estimate the amount of energy based on the recorded battery current and voltage values. Since current and voltage values are recorded at least once every second, the above formula provides a high accuracy estimate. And for diesel vehicle, we can compute the amount of fuel used between 2 consecutive data points as the change in the total amount of fuel we used. The next step in our workflow is to map the GPS location to road segments. The recorded vehicle locations are inherently noisy since they are based on GPS. For example, sometimes the locations fall onto the streets or parking lots where the bus cannot even drive. The noise represents a significant challenge for computing accurate travel distances and for integrating the time series with other data sources. So to mitigate this noise, we use a street level map of Chattanooga from OpenStreetMap, and then we combine the vehicle's recorded locations to a real street address. OSM divides each road into multiple segments and assigns them an unique OSM feature ID. We map each recorded GPS location to an OSM feature. For a particular location, we consider a set of nearby OSM feature based on the geographical distance. And for each nearby OSM feature, we count how many times The preceding and following data points were also near this feature. And finally, we select the feature that is near the most data points. Here we evaluate our algorithm to see how well it behaves with different level of noise. Since we do not have ground truth for the correct mapping in our GPS-based dataset, we create a test set with known ground truth. And then we add random noise to these locations. The noise is generated using a two-dimensional Gaussian distribution with zero mean. We vary the standard deviation of noise between 1 meter to 110 meters in both directions. Finally, we map the noisy location to road segments using our algorithm and measure the accuracy as the ratio of correctly mapped locations. The top figure shows 3 maps where we have mapped the locations to street. One of them is without noise, one of them is with 14-meter standard deviation noise, and another one is with 28-meter standard deviation noise. The bottom figure shows the accuracy of mapping with varying level of noise. And as expected, the accuracy of the algorithm decreases as the level of noise increases. However, for reasonable noise level, it performs very well. With 14-meter standard deviation, it can still correctly map up to 85% of locations. The next step in our data processing workflow is to generate the samples. And to generate a set of samples, we divide the time series of each bus based on the traveled road segment. Specifically, for each bus, we treat a maximal continuous travel on a particular road segment as one sample. Here in the picture, we can see that the bus is traveling from one street to another, and the continuous travel on one street, actually one particular OSM feature, is considered as one sample. Each sample has a starting data point, ending data point, the sum of amount of energy or fuel used between them, and the total time taken for the continuous travel. Next, we calculate the travel distance. Since the GPS-based locations are noisy, we combine them with OSM to calculate the distance traveled for each sample accurately. First, for each sample, we obtain the geometry of the corresponding road segment from OpenStreetMap. This geometry is a list of contiguous line segments. Because the bus does not necessarily travel the complete distance of the road segment, it can turn on a different street before reaching the end of the road segment, we need to identify the first and last line segments that the bus actually traveled. We calculate the distance between each line segment and the starting and end points of the sample. And then we identify the indices of the line segments that are closest to the starting and end points. Finally, to calculate the distance, we take the distance, partial distance on starting line segment, the full distance on all line segments in between, and the partial distance on ending line segment. Finally, we want to remove the outliers. Even though the current and voltage values are almost always correctly recorded, we did find a few data points that have erroneous or missing values, which results in extremely low negative energy consumption estimates. Many electric vehicles can recharge from braking, so energy consumption can in fact be negative for some shorter samples when the bus is slowing down or going downhill. However, the erroneous values that we have results in implausibly low values, so we remove them from our sample. And finally, when we have all the clean samples, we add different features to the data set. One of them is elevation. We calculate the distance between the elevation at the start and end point of each sample, and the change in elevation captures the potential energy gained or lost during the travel. And then we incorporate traffic. Our timestamp traffic data has a unique identifier called traffic message channel, or TMC. Based on the geometry of the TMC and the shortest path from an OSM feature to a TMC, we have mapped the OSM feature to the TMCs. Since our goal is to provide prediction for planning transit operation in advance, we cannot rely on real-time traffic for energy use prediction. So to compute average traffic condition for each TMC segment for each hour of the day or each day of the week, based on the historical data, we use the hourly averages as traffic prediction. And then we add two features from the traffic prediction to our samples. The features are speed ratio and jam factor. Speed ratio is the actual traffic speed over the free flow speed, and the values range from around 0 to around 1, where around 1 means light or no traffic, and the values around 0 mean very heavy traffic. And the jam factor indicates the expected quality of travel, ranging from 0 to 10, 10 being it's a road closure. Then we incorporate the traffic weather data. Similar to traffic, we cannot rely on real-time data for weather, so we compute hourly weather predictions for each station based on recorded historical weather data. There are multiple weather stations in Chattanooga. For each sample, we compute the distance between the sample and the weather station and add the predicted weather feature for the closest station to the sample. Our weather dataset has a number of features, but we use temperature, humidity, visibility, wind speed, and precipitation. This concludes our data processing workflow. Then we move on to our macroscopic energy prediction. For the energy prediction, we have been using these particular features. Some of the features are categorical. For the categorical variables, we have mapped them into binary features using one-hot encoding. We have tried with different models. One of them is deep neural network. We found that for deep neural network, different network structure work best for different types of vehicle. For electric vehicles, the best model has one input, two hidden layers, and one output layer. But for diesel vehicles, the best model has 3 more hidden layers. Since there is no particular rule to find a network architecture, we actually experimentally evaluated a variety of architectures and found that these models work the best on our dataset. We have used sigmoid activation function in all the hidden layers and linear activation in output layer. We optimize the models using the Adam optimizer with learning rate 0.001, and we evaluate the models based on the minimum squared error. We also implement decision tree and linear regression. Linear regression shows the direct relation between the input variables and target features. We use the implementation provided by the scikit library. We also implement a different structure, tree-like structure decision tree. And we also used for decision tree the implementation provided by a Python library, but we tweaked some of the parameters such as the depth of the tree and the minimum number of samples required at a leaf node. And we evaluated the decision tree based on the MSE values. Now moving on to the prediction results. One of the key questions that we studied is which factors are the most useful for predicting energy use. In the figure, we can see the prediction error for deep neural network with weather, traffic, and elevation feature, as well as some of their combinations. The lower value actually means the more accurate prediction here. As you can see, the weather features are the least useful for both diesel and electric vehicles. On the other hand, elevation features are useful for both types. The most interesting observation here is that the traffic features are significant for diesel vehicles, but not for electric ones. We believe that this difference is explained by regenerative braking. Since frequent stops due to traffic may have a lower energy impact, we see that traffic is not that significant of a factor for electric vehicles. Next, we evaluate our 3 different machine learning models based on how well they predict energy use for samples. We are predicting for a trip by dividing the trip into series of samples, but these samples are very short in both distance and duration, which presents a challenging problem for the prediction. Here, the figures show the minimum squared error and minimum absolute error for diesel vehicles. And based on the MSE score, we can see that the deep neural network outperforms the other 2 models. And similarly, for electric vehicles, we can see that the deep neural network performs the best. Since we optimized our models based on MSE score, I think that can explain the slightly similar performance of deep neural network and decision tree model in case of mean absolute error. Now, in order to study how well our model performs with respect to predicting energy use for longer trips, we divide our time series into varying lengths of trips. The length of these longer trips vary between 10 minutes to 6 hours. For each trip, we generate a set of samples, as we described earlier, use our models to predict energy use, and then compare the sum of this prediction to the actual energy use of the trip. Here, the figure shows the relative prediction error for trips of various lengths. We can see that the relative prediction error for trips of various lengths for the deep neural network, the decision tree model, and linear regression model. For each length, we plot an average error value computed over many trips. We see that the relative prediction error is generally lower for longer trips. This is expected as the individual errors of large number of samples cancel each other out with an unbiased prediction model. As you can see, the longer the trip, the lower the prediction error, which means that our predictors are well suited for large scale and long-term planning purposes. We can also see that the neural networks generally perform as well as or better than the other machine learning models. But for electric vehicles, the ANN and DT perform, decision tree perform equally well for most trip lengths. Finally, to conclude, we presented a framework for the data-driven prediction of the energy use of vehicle and electric and diesel vehicles, which we evaluated on real-world data collected from a transit fleet. Our study shows that it's possible to collect, aggregate, and process heterogeneous transit data effectively. We found that generally the deep neural network performed best for predicting energy use. And for diesel buses, we achieved the best result using 21 predictor variables. These variables are travel distance, road type features, elevation change, 3 weather feature, and 2 traffic feature. And for electric buses, we achieved the best result by including 2 more weather features. We also found that the relative prediction error is lower for longer trips, which facilitates the long-term planning of transit operation. I want to thank the reviewers for their valuable comments, and thank you so much for your attention. If you want to know more about the project, you can visit the website, and I have put the link in this slide. And if you have any question, please feel free to reach me out. Thank you so much.